Today we're going to be learning about how to determine a rate law from initial rate data. The first thing that I do when I see a multi-layered, multi-part question like this is I just take it one step at a time. Our first part of the question asks, what is the rate of disappearance of B in trial 2? So the first thing I think about is, well, why am I just concerned about part B? Then I realize up here in the first row of information, I have a rate of formation of C, which is not B. So I'm going to check my given chemical reaction right here. And it looks like B is going to disappear twice as fast as C is forming. You can write these kinds of relationships using an equation found in our textbook. We can usually write the rate of disappearance as negative change of A over time negative 1/2, using that coefficient in front of B, change of B over time, equal to the positive change of C over time. We can use this relationship to see that the rate of B will be twice as big of C. Check right here. To isolate the rate of B in this equation, we would have to multiply the other side times 2. And we'll end up with the answer for part A being the rate of B is equal to negative 1.4 times 10 to the negative 3. Please notice that it's important to include the negative sign here because this species is disappearing, not forming. For part B and for part C, we're going to need to use our data table to compare what happens when we double or triple or even quadruple our starting concentrations to see what happens to our rate of formation. So the first thing we need to do is find out what the order is with respect to A. This phrase, with respect to, means we need to focus on when A is changing, what does A do? So what I'm going to do is I'm going to find a time when B is doing nothing, which seems like trials 1 and 3. And then I will see what happens to A, and it looks like the numbers here are doubling. Sometimes the numbers aren't as easy as 12 and 24 being an obvious double. Sometimes they're a little bit more interesting, and we'll handle those cases in a lot of our practice problems. So here's what I'm going to do for part B. I'm going to look at trial 1 versus trial 3 and just make a fraction out of what I see happening in the numbers. I see that between these two pieces, we double. And I'm interested in what this exponent up here is going to be. Then I check what happens with the B, and nothing happens here. It's really important to make sure that you isolate something that's not moving unless you have a problem where you have no choice to do that. And then we're going to see what happens to our rate of formation here. And sometimes these can be a little hard to see if you didn't know that 36 is the double of 18. What I would do in your calculator is put the big number over the small number and see if it gives you a whole number you recognize. In this case, 18 is half of 36, so we'll equal that. Now we can do some simplification of our math to see what our exponent x is. We'll see that x is equal to 1 to make this equation true, and that 1 ends up going into our rate law like that. We don't have to write the 1, however, because it's implied. Now to move on to part C. In part C, we do the same thing, but we need to focus on a different set of data to find when B is changing. So we're going to now focus on trials 1 and 2, where A stays the same and B changes. We'll set up our little equation again, where we have nothing happening, nothing changing in our first area. And we see that we have another doubling situation. But then when we check out what happens in the rate, we see that we have this interesting number here. Now, maybe you're more clever than I am, but I needed to put 7.2 divided by 1.8 in my calculator to just double check that that meant that that fraction needed to be 1 over 4. 72 would be 4 times 18. Now we can do some simple math and see if I really want this part of my equation to make sense, my exponent needs to be 2. So with respect to B, we're going to be second order. Now we're pretty much ready to answer part D. Part D just means write out what you know and understand about the relationships in this problem in an organized way. Rate laws always start by saying the word rate equals, and then we're going to write the rate constant, which we don't know yet, A with the implied 1 times B squared. Done. Now it's time to find that rate constant K. We're going to focus on just one line of information. You can choose your favorite line of information. I usually like to choose row number 1 so I don't miss numbers or accidentally jump lines while I'm doing my math. So here's part E. I'll just choose the rate is equal to 1.8 times 10 to the negative 4 equals my mystery rate constant, 1.2 times 10 to the second, negative second, times 1.2 times 10 to the negative 2 squared. Awesome. Do some math in your calculator and we find out that the K in this case is equal to 104. Now you'd be like, hey, cool, I have this awesome number. Unfortunately, we do need to make sure that we round. And the easiest way to do that is to put this into scientific notation. And as always, it's very important to report any kind of constant or a rate with the proper units. And in this case, our rate constant will have a unit of 1 over molarity squared times seconds. Now for our last question, part F, we need to use our last line of data in trial 4. What is the initial rate of formation of C in trial 4? So we just need to put in all of the numbers we already know and plug and chug. So we're going to be focusing our attention on this last line of data to find our unknown for part F, and our rate will be equal to 1.0 times 10 to the 2, our rate constant we calculated, which is good for any of these situations as long as it's the same temperature, times 2.4 times 10 to the negative 2, that value for the initial concentration of A, and 6.0 times 10 to the negative 1, the value for B. And since it's the B, we need to square it. And then our answer for the rate of trial 4 will be 8.6 times 10 to the negative 1. not forgetting our unit, molarity per second. I really hope that this video helps you navigate these AP style FRQs.